Ja, ganz herzlichen Dank. Und ich habe Ihnen schon gesagt, Ihr Institut war mir lange bekannt und ich habe mich immer gefragt, what on earth happens there? Ja, der Name war nicht so leicht zu entschlüsseln, was da wirklich passiert. Und es ist sehr schön, hier zu sein. Frage, ist es okay, wenn ich in Englisch spreche? Weil ich für das Recording, ich stelle die immer ganz gerne auf YouTube und es ist immer erstaunlich, wie viele junge Leute weltweit sich die Talks angucken. Yeah, so I'm talking about a phenomenon which, I mean, we have Mark Whitman here, of course, has long been neglected. And it's the inner time of the brain. And that's very important because usually in cognitive science or cognitive neuroscience, you only look for how we perceive and cognize the outer time in the environment, but not that the brain has its own inner time. And that's why it's really important. And that's why I say time is relevant for the mind. And if you ask me in my optimistic moment, I said, time is everything. So my really focus in that part of, because it shapes our mental state / spatial temporal neuroscience. So, however, time is not time. Look at this. You have time scales. And my talk will largely focus on time scales. What are time scales? Duration. You have the duration of a heartbeat. It's 1 second time scale. You have the time scales of consciousness. 10, 30 milliseconds to max 5 minutes. Mark knows this much better than I do. You have the time scales of the brain, which are much larger than the time scales of consciousness. And we have the time scales of the environment. Let's see geology, seismic earth waves. We cannot perceive them. Just a couple of weeks ago, I read a paper about elephants. They have very much infraslow frequency fluctuation. They can only understand the other, I wanted to say other person, that's a Freudian slip, over 50 meters. So if the elephant is over there, they can understand each other. If you're over there, I have no idea what you're talking about. Yeah, so really important because they determine and shape our possible relation to the environment / consciousness. So my talk will focus on the inner time within the brain. First, I want to say a little bit, and I say the main claim is basically, no surprise here for many of you, that the inner time of the brain is really absolute key for mental features. And by mental features, I have a large umbrella term. I do not only mean consciousness, I also mean self, thoughts, emotions. You will see all these examples throughout my talk. So when you look at my website and you say, my God, this Northoff could never really decide what he researches, is all these different things. Ultimately, it's very simple because it's just brain-mind subjective features. Yeah, what is your subjective experience, perception of yourself, of your consciousness, of emotions? So I'm interested in this subjective experiential component. And I say this as explicitly here in this context. If I were saying this as explicitly in Canada or US, people would look at me, what a strange guy you are, you don't do science. That's the kind of reaction one often gets. So and then I will show you some examples, timescale, self and consciousness. I will show you also some recent findings on speed and emotions, and then on temporal precision. So basically, what you can already see here in the outline, I try to decompose the inner time into different dimensions: speed, precision, regularity, irregularity, and then I link that to the mental phenomena and also to specific mental disorder, of which I will touch briefly upon. But if you're interested in on that side of our research for tomorrow night, where I present a very simplified version because it's medical doctors and a lot of practitioners. But there you get an idea what I mean by spatial temporal psychiatry and spatial temporal psychopathology. So I don't need to tell you, I'm a big fan of metaphors. Always in Canada and US, it doesn't fly so well. When you go to China, Japan, they understand these metaphors very well. It's a remarkable cultural difference. And so for me, the iceberg, of course, there's a layer-like organization of the iceberg. Yeah, that's, you all this, the Freudian stuff and all that. And I'm a big fan of this layer organization. And indeed, in my recent large textbook, I indeed develop a dynamic layer model of brain. So basically, that's what you will hear from me. So then I already indicated that. So first, what we usually do when we hear about time in cognitive psychology, cognitive neuroscience, is about the perception of outer time. Yeah, so let's say there's a car passing by and how fast you perceive the speed. You have all these duration experiments. Again, I don't need to say much of that here in this context. And that's basically what you say. But the question is, where is the subjective component, the perception experience of that coming from? That's what I'm after. Yeah. So that's so you can have the same kind of, let's say, inner voice, but you experience in a completely different way. And that makes a difference between a psychotic patient and a normal patient, because we all have these kind of phenomena. So it's the meaning with you associated with itself. And you already see, this is what I say, okay, that's your inner time within the brain itself. So now, interestingly, when you look into the history of philosophy, you look into Immanuel Kant's Critique of Pure Reason, and what do you see in the first part of that book? The Transcendental Aesthetics, he distinguishes inner and outer time. And that was actually historically, as far as I read it as a philosopher now, really the starting point for Husserl and his phenomenology, and then his inner time consciousness. So, and I, standing on the shoulders of these guys, I extended that. So when I read Kant again in 2003, of course, in my philosophy student times, I read him. And then I read it again, and then it dawned on me, okay, now we need to change the whole neuroscience and everything, because it's really this inner time, and that was also the time when the spontaneous brain activity regulated the fault mode network. I have a lot to say to that, but which I will not do that here now. So that is really important. And then you have sort of also, basically here it's outer time, can be called a container view of time. And here, this is a paper in the 2020 Physics and Life Review, where we say it's a construction time. It's a construction of time. So your inner brain, your brain continuously constructs its own inner time and also space. Here I focus on the time. You can look on my website or in the discussion about the spatial dimension, which is a little bit more difficult and tricky. It took me many more years to get there. So you really have an inner time, and that inner time and space is matched and compared with the outer time and space. So we have a huge line of research going on this matching process. Yeah, we call this temporal spatial alignment. Signpost in current neuroscience is the entrainment, which is sort of in a very short time scale in a rhythmic scale, and in a larger, we say it's a temporal spatial alignment. And that alignment to the stochastics of the external input is absolutely clear. And when you speak about the random distribution of the external input, you already have a time component because it's a time series. So when you perceive me, your brain probably encodes the temporal stochastics of my language and my movements. Yeah, and by encoding, let's say, and now if I'm discoordinated, you might encode that too, but it's hard for me to simulate that. So, and then, so now then the next question, okay, yeah, Northoff, nice, go home, but you're a philosopher, we want some neuroscience here, we want some flesh to the bones. Okay, and how can you measure the inner time and space? So, and that's really a key point, because that's where I look towards physics, in particular electrical engineering, and even more specific, signal processing. So that's why we do all these strange measures, which are not commonplace in current neuroscience. So, but when you go speak with engineers, for them it's normal, and physicists. So I show you a little bit now. I'm moving because I was said not to move too much because of the camera. So you have a time series spontaneous brain activity. And remarkably, when you do a fast Fourier or a Welsh transform, you basically get a power spectrum, and you get a more power in the slower frequency and in the less power in the faster frequency. And that follows what is called a scale-free, scale invariant distribution. So if you do a log-log, you have here the power, you have here the frequency, you have the same temporal structure of your power spectrum across the different parts of here. So in that, what you can measure with, for instance, the power law exponent is basically the temporal structure of your power spectrum, the distribution between slow and fast frequency power. Now, you say again, we're not interested in that. You should be. From here, it's not that far towards the Mediterranean. Look at the waves, and you see exactly that pattern. You see large waves, very powerful. You're afraid of them when you step in. And then you have some small waves, you're not afraid at all. Look at seismic earth waves, same thing. Yeah, so that's a natural phenomenon. And the scale freeness, I think I show later some data. It's really important that we live in a scale-free environment is hugely important for consciousness. We wouldn't have that. Then another measure, which one of my favorites is here, what is called the autocorrelation window. It's basically the index of your how much a process lasts. As I already said, intrinsic neural timescale. There's a lot of cognitive view on the intrinsic timescales by the group around Hasso, who did a lot of movie segmentation and speech segmentation. But the brain has its own intrinsic, already in the resting state, intrinsic timescales, and you can measure that, which is called autocorrelation function, meaning how long does the signal correlates with itself over time. So a heartbeat correlates with itself after 500 milliseconds, but after 1 second is over, because that's the duration of the heartbeat. So that's basically, and you measure that through the half-life. This is the autocorrelation window you will see. And there are various other measures which are in there because they describe distinct aspects of your signal over time. So this is very important if you want to understand me and our research, that I really try to go into subdivide, slice up what you mean by time in different aspects without losing the overall phenomenon. So that's really important. And the more specific you slice up into distinct components and features of your time space, the more specific you can link to specific mental features. I will show you some of that in the following. So that was basically the first part, what is inner time. So take home message, the brain has its own continuous inner time, which is continuously produces, and with that it encounters the outer time. So if your inner time is very slow and you're very tired, of course it's Northoff, I mean, you're just telling some stupid stuff. So your inner time is very slow, it will not match with the faster outer time you perceive. Yeah, mismatch, you will have no attention, no memory, and say, okay, boring talk, should go back to Canada. Yeah. However, if let's say you can really synchronize with me, and that's also why I like to walk around, because it sort of captures people's attention for myself, then you can try to synchronize with me, and then you probably get a message. It's the same as when you're dancing, you dance in tune with the rhythm, and you feel the groove of the music. Yeah, that's what it is. That's why, for me, this temporal spatial alignment is key for consciousness. So now I will show you some of that applied. So I don't go into we also have a whole line of basic research on these timescales, which I spare you, but I go right into some application for the mental features. So I think I already made it clear what are timescales, the time for a process or sequence of events. Your breathing time scale is much longer. Yeah, it's about 9 to 10 seconds than the time scale of a heartbeat, which is 1 second, and so forth. And your brain has an abundance of time scales. That's the amazing thing of the brain. So, and that's what is called here, again, quoted, intrinsic neural time scale, the time window in which, and now slightly different from the information angle, in which prior information from ongoing activity or stimulus related can affect the processing of newly arriving information. So here I put it more into an input processing, but it's the same thing. Yeah. So, and that's very important. Now, just if you're versed in phenomenology, in a time consciousness, Husserl distinguished between protension, retention, and primal presentation, and that's a continuous overlap. What is in the present goes into the past, into the retention, and so on. There's a continuum, and that continuum of inner time consciousness is probably here key for this kind of process because they overlap. So, how can you measure it? It's typical here. You have time lags, so you do a time series of your signal. The signal could be a behavioral signal, could be a neuronal signal, could be a breathing signal, could be a heartbeat signal, and could also be an input signal. So that's the beauty of these measures. You can apply them cross-level. And we are really working on this kind of stuff. Yeah, and then you see the dynamic connections between, let's say, for instance, neuronal level and behavior level. We just had a paper on that. Yeah, where we have really corresponding measure. We call that common currency. So how do you measure that? So you have here a signal, and then you calculate basically how much similar is the signal over the time lags. Yeah, the time lags could be your sampling points. Yeah, in EEG, obviously higher, in fMRI less. And you see basically, and of course, the longer the the distance, the less the signal is correlating with itself. And then by definition, that comes from physics, half-life, that basically you say after 50% of the correlation, that's what you determine as the ACW 50. We call that, we introduce another measurement when the signal crosses the zero line. Yeah, and then you can also measure the slope of the curve, but I leave that for the specifics. So there are various ways of calculating this. We just published an open software on this, on different measures here, which is probably not that relevant for you. You can also, you have model-free measures, methods, or model-based method on the Bayesian stuff. So I leave that just, you can look that up on our website. And then why are these intrinsic timescales so important? So here you have what is called, probably many of you know this unimodal transmodal distinction. The core of the brain is the default mode network and the higher order association areas. And you see that is here all in red. And the blue stuff is the unimodal region, sensory-motor, and there's a certain gradient between them. Functional connectivity size, that what Margulis showed, we and others showed that gradient also for the time scale. And that's very important. So your time scales are shorter in the sensory and motor regions and much longer in the higher order and association region. And the DMN, as usual, sits at the top of the hierarchy and has the longest time scale. So, and that's very important. So you can already see here there's also a spatial component, topography. Yeah, go into physics, time and space go together. Yeah, of course, there's always the question who is first. When you would have asked me at the various stage of my professional life, at some point I would have said time earlier. In 2014, I wrote 2 big books, Unlocking the Brain. I said, okay, they're similar, and now our data confirm more and more that I go with time as the driving of space. So here you see the difference between the blue, the unimodal regions, and the transmodal regions. We did this for 3 different anatomical templates, and you always see that the ACW is really shorter in the sensory. And that makes sense, because your sensory region must continuously encode, or I'm not allowed to work further, the faster stimuli. Yeah, so that makes sense. And it's not fully clear why the higher order regions really have longer time scale, whether it's an intrinsic feature or just due to the filtering of the input processing. So that I leave that open. So that's, but here you currently see, look, you look at the topography of these time scales and you can already infer what must happen if these time scales are, for instance, altered. So I'm always after the brain's intrinsic features. So now I say, why are these relevant for mental features? Because I went into all this engineering, not because of the sake for the engineering, but I wanted to link to mental features. And one of the key features is the sense of self. So when I speak of self, I do not mean a higher order cognitive elaboration, a self-referentiality. That's many people understood us like that. But ultimately what I mean is a basic subjectivity. Yeah, it's your basic experience. So when you hear me, you have a feeling of boredom. And I'm after this feeling of boredom. Yeah, not the boredom itself, but the feeling of boredom. Yeah, so that's what for me always the self. And one of the things what's remarkable that in the earlier 20 years ago, that we really observed, we and others, there's a strong neural overlap between self regions, cortical midline structures, and high resting state activity default mode network. So, and we took this very seriously because if there's really such an overlap, then this high level of spontaneous activity must already be, even in the resting state, index some kind of basic self or subjectivity. Yeah. And so that's why I said, okay, and then the next question is, what are the features by means of which the spontaneous activity relates to the sense of self or subjectivity? So, and then I came up with the spatial and temporal dimension. So that's really why I said, well, I do this, and that's the spatial temporal neuroscience, because that's why I say, look, that's your key feature through which the brain adds something to the objective input processing, and that makes it subjective. So, and then, of course, the next thing when you say, yeah, Northoff, is that so, then you need to investigate the temporal and spatial features of the brain, intrinsic features, in resting state, whether they predict your sense of self. And that's exactly what I show you here. So here we calculated this autocorrelation function. You here see the legs. The longer the legs, the less correlation. Here you see the distribution, of course, as always, intersubject variability. And then because it was in the resting state, we couldn't do a task. So we did a self-consciousness scale that has 3 dimensions, private, public, social. And you see in the private self-consciousness, you had a good correlation. We did this in both EEG as well as in fMRI. And with source analysis in EEG and in fMRI, of course, we had the location, particularly in the cortical midline structure. So that was thought, it was wow, your spontaneous activities, temporal features predict your self-consciousness. That we replicated that, other people replicated that in both fMRI and EEG. So then the next step, how does that affect your psychological functions? If your timescales are relevant here, maybe if you build in some temporal delays in a task, if your time scales here, in particular the longer time scale, meaning the more longer time scale you have, the higher your sense of private self-consciousness. Meaning yourself, metaphorically speaking, is stability. Temporal stability over time, temporal continuity. And that's exactly, I think, we experience our sense of self, or not if you have mental disorders. So then we said, okay, maybe we need a task where we build in some temporal delays and see whether the autocorrelation window, the duration of the temporal activity, self-correlation, should predict the behavioral data from these temporal delays. So here it was a first attempt to say, is the duration on the neuronal level related to the duration on the psychological level? Yeah. So you will see in my theorizing that's absolutely key. So, and that's exactly what we did. So here we took a very really nice task on self-prioritization. Zui, she's in Aberdeen, but comes originally from China. And she developed the self-prioritization task. So what do? So you get a shape, and you need to either associate with yourself, a friend, or another person. Yeah. So that's basically what they call shape-label association. And why do they do that? Because she wanted to avoid that you tap some intrinsic features within the stimulus. So sometimes this one is associated with you, sometimes the same shape is associated with another person. And what you see purely psychologically, you see an advantage of self-referential stimuli, higher accuracy, faster reaction. I mean, it's really amazing. I didn't believe that the first years because I couldn't imagine, but indeed it's true. So ourself is important, no doubt. But what we did a temporal delay. So say, okay, that's usually what they present, but we inserted a temporal delay here because, okay, here's a shape, and we delay the process and then associate it with yourself. So we put a temporal component to the shape label association, and then here 40, 120, 700 millisecond, and we said, okay, maybe even in the resting state, how people deal with this delay and how much it impacts the accuracy and self-reference or self-prioritization, as Zui says, maybe that is related to your temporal windows in the brain. And that's exactly what you can see here. So here you say, okay, you see this, and then you need to click and say whether it's accurate or not. So you get sort of, okay, yeah, it's an association. So here, so you start a block of trials, say, okay, this is your U association. Yeah. And then you get various combination of this shape with another person or you, and you get also some other shapes, circle or something like that. And you always need to say which is the correct association, which was told to you at the beginning of the block. Yeah. So it's really, and that's what you wanted to measure. How do you, now in my language, how do you associate an external input with yourself? Yeah. So basically, now if you conceptualize that, okay, you have an external input, how is that related to your internal self? Without the input itself carrying a self-specific component. Yeah. Because this continuously changes. Yeah. So basically what you really test, how is an external input associated with an internal self? So, and then we build, and that's what you usually get, but then we build a delay between the shape and whether it's associated with you or not. Yeah. So basically, we built in this temporal delay because we want to see, is this temporal delay related to the temporal delays in the brain? And we took these because these are exactly the temporal delays we can still measure. Here we're in the delta range, here we're in the alpha range, which we can still also measure with the ACW, the autocorrelation window in the brain. Yeah, that's very important. So you have a matching of the duration. So, and then you see in the paper, we called it concurrency because the duration is shared by neuronal and psychological features. Yeah, that's important. Basically, the duration you measure on the neuronal level here are related to the psychological duration, how well you can cope with them or not. So, and then we said, okay, so this was our resting state. Now, how does the autocorrelation window changes from rest to task, and how is that related to your sense of self? So you see, really, we built this up very carefully. So this is another task which we use here. So now we presented a continuous task. So we presented a self-narrative, 8 minutes, resting, of course, no narrative in the resting state, and a non-self narrative, which was the same for all subjects. Yeah, and they had to listen to their thing. And it was nice. It was a data set which we got from other people. The nice thing what we could do, they had also outside the EEG, they had continuous behavioral assessment. So continuous, so they always had to move a cursor when something happened in the movie and that changed their emotion. So that's what I like, because then you get a time series of your behavior and you get a lot of data points. So, and that's exactly what you can see, and amazing. So it was basically a 2D screen, and you get emotional, how much emotional involvement you had. And you see already, even for the self, just purely behavioral on the screen, you have more movement, you have more distance, you move to distant thing. Here we have this variability. You have also more variability in your movement, very important. And here you have also the speed, velocity. So you again see, this is basically here, particularly these two, is the dynamic decomposition of your behavior. So this is, for me, I'm still dreaming of the optimal experiment where you have a really good time series, let's say, of a conscious versus unconscious data set, and you can make a time series out of that, and you expect that that fluctuation relates to the fluctuation in your brain of your temporal windows. So now, interestingly here, this is the autocorrelation window in this study. You can see in the rest you have the shortest. When the external input comes, your autocorrelation window lengthens. That's a common observation, which you also observe in attention and working memory. It's probably due to the fact that there is an external stimulus, a continuous external stimulus, which you need to integrate. And if you integrate, of course, you lengthen your temporal window. So imagine if this window now, we have only the small window, you can only see maybe here the antenna and nothing else, but the larger window, you can see, okay, it's part of the house. And if it weren't those windows, then I would say, I don't know, is this a block, is this a house or a single house? Now, if you have a really big window, then I finally would know what happens here and what happens here. Yeah, but you don't allow this. Yeah, I'm joking. So that's what we do. So, but what is interesting again, in the self movie, in the self story, it was longer than in the other story. So your self really makes a temporal spatial difference on neuronal and behavior level, on the neuronal level, on the behavior level. And you see also here the topo maps, which I'm always, this is 64 electrodes. I'm always careful. Reviewers always want to seize it, but I'm always careful with the inference of spatial locations. So then you say, yeah, what on earth does this ACW do? Is this really related to the temporal integration of different inputs? That you can test. So we had another paradigm here. So this is a self-effacement paradigm. So it's a morphing paradigms. You start with your own face, and then it's gradually morphed into another person's face. Over, you see here's the duration, 10 to 15 seconds. You start with yourself, end with another person, or the other way around, and then people have to click, at which point they have the feeling their own self is no longer visible, and another person's start. So, and then here we said, okay, and this is really, it measures temporal integration. Yeah, because if you integrate all these stimuli, then you say, okay, the other person is myself. Yeah, if you integrate them too long. So it's really, we're testing for temporal integration on the psychological level. And then, of course, you can imagine what we did. We did also that the same on the neuronal level. And what we indeed observed, we saw again, sort of, we do a parametric evaluation of the self. You saw again a prolongation of your autocorrelation window during the task compared to the rest. So because we included the temporal integration in the psychological level, we can say maybe the prolongation of the ACW in the task has something to do with temporal integration. So yeah, but then you say, Northoff, you just infer from the psychological to neuronal level. You need to show it on the neuronal level. So this is, of course, the limits of brain imaging. This is where we now do a lot of computational modeling. So, and I tell you what we did here. So here we did a large-scale biophysical model, the Chaudhuri model from the Wang Group 2015 Neuron published. And what we did in the model, so okay, we presented a short input. And we wanted to see whether the input duration is represented in the neuronal activity duration. So now I go from input duration to neuronal duration. Yeah, before we had from neuronal duration from output duration. So now I do the opposite on the other end, and you see in early visual cortex, this is all model simulation, you see really a very nice representation of the duration of the input in the neuronal activity. But now go to higher order regions, you have a gradually smoothing, and here in 24C anterior cingulate cortex, you see a complete smoothing. Yeah, you don't make a difference anymore. So meaning here you really perceive this, but your anterior cingulate is just one smoothed, blurred thing when I do this. Yeah, and then we tested this here also with a long input, same thing. And then, of course, we calculated the ACW for these regions. For V1, it's much shorter than the long ACW. And then the one who did the simulation, Yazir Chatal, is the second. He had a very brilliant idea. I loved it. So he said, in the model, there's a hierarchy index. And in one of the algorithms, there's a little hierarchy index, H. And he said, a unimodal transmodal hierarchy index, which you can see here. Okay, how about we just set that hierarchy index to 0? And what you see suddenly there's no difference anymore between the higher order region, here 24C, and V1. So meaning that the difference in time scales here in the duration may be a matter of the topographic differentiation. So here you see topography is important. Yeah? And in mental disorders, you see changes in the topography. So I found this is now on the neuronal level, that maybe this ACW thing is really related to the duration, and it has a certain topographic hierarchy. So this is obviously temporal integration. So then you say, okay, what are the mechanisms of the self? So I show you what you can do with the computational modeling here. So one of my students in Turkey, really brilliant idea, I'll show you. So first, what we established based on a large-scale, really large-scale meta-analysis of different imaging studies on the self, we established a 3-layer topography. We call it like that. So this is based on fMRI data, and you have interoceptive processing, your interoceptive self, when your stomach doesn't like you, or your heartbeat awareness, of course you all know that. And you see these typical regions. This is based on the meta-analysis, bilateral insula, thalamus, dorsal anterior cingulate. So largely regions of the salience network, which makes sense because these regions are sort of involved in the intro and exoceptive coupling. It's not just interoceptive processing. It's really, I think for me, it's an intro-exoceptive coupling. Then you had also exoceptive processing regions. This is for those who know the literature, so all the studies by Blanke, the proprioceptive illusions, body illusion, and limb illusion and things like that. And they involved, again, the salience network regions plus additional region, bilateral TPJ, temporal parietal junction, right premotor cortex, anterior medial prefrontal cortex. And then we had all those paradigms which were about your cognitive self-reference / mental self. You see all the cortical midline structures and all the other regions. And what is amazing, it's really a nested model. So the regions here are recapitulated in the regions here, plus some additional regions are added. And these regions are recapitulated here. Some additional regions are added. So it's really a nested organism. It's like the Russian dolls. It's amazing. Yeah. And these are completely independent data sets on which this is based. So this is not just a carryover thing. So it's really a nested organism. I don't think I have my beloved Russian dolls here today. So I usually show them in my talks because I like them so much. And it's really a nestedness. And now we're trying, I will not show this here, trying to exploit this nested organization also for psychotic differential diagnosis. You have various papers in depression and schizophrenia. You have differential changes of this three-layer topography of self. However, so what I want to do here is now look. So what this student did, he said, okay, these are all self regions, and I compare them to all non-self regions. Yeah, and he said, okay, look, all my self regions have a longer ACW, longer time window, which is no surprise, than the non-self region. So he just wanted to say where there's an intrinsic non-self self topography in your brain. Yeah, and the emphasis, it's inbuilt. Yeah, if you lose that, you lose yourself, and ultimately also you lose the features of the brain. So then he said, okay, we do, and what are the biological features of that? That's basically the question I want to go here. So then he noticed another large-scale biophysical model, the Wilson-Cohen model, and he simulated that. And what you can do in the, and then he fitted the individual subjects' data. This was, and he fitted the data, and we had a good fit. You use the power spectrum. And then he calculated three measures. He calculated the myelin content, which is lower in the higher order and in the self regions than in the non-self. He also included here the transmodal unimodal. Here he calculated the ACW. You see here a very nice gradient from the transmodal regions of the self, the transmodal non-self regions, the unimodal self regions, and the unimodal non-self. So you really see, even within uni and transmodal, you see a distinction between self and non-self. So the self is really an intrinsic feature of the topography. And then we also calculated the global activity. I spare you the detail with the global signal correlation. So now, then he simulated in the model, we said, what could be potential features which relate physiologically to the ACW, to the timescales. And we particularly focused on two features, on intra-regional recurrent connection. So we have always the same, basically your stimulus input into a region circulates within the activity of the region. That's what you call recurrent processing, intra-region. There are various meanings of recurrence. For instance, Lamme in consciousness, in the consciousness field has this different meaning. So it's very important. So here we basically mean intra-regional connect with intra-regional processing, the duration of the stimulus processing. And of course, the level of neuronal excitation. And then you can see in the model, okay, you play with these two measures, you fix the recurrence, you fix the excitation, and you cannot replicate this nice curve. So meaning, okay, it doesn't work. Then we say, okay, we fix the recurrence and we just look for neural excitation. Okay, curve is a little better, but still doesn't match. Now, if you keep both flexible and adapt then those measures to the empirical data, then you finally get the curve. Yeah. So that tells you that really intra-regional recurrence and the level of neural excitation is important for this kind of topographic pattern. So that gives you an idea about the physiological features of the ACW. So you really have, remember, I started with the mental, now I go down to the physiological, and I don't need to tell you, highly relevant for mental disorders. That's what we're trying to work on it. So what does this mean psychologically? He added this very nice figure. So here you have the neurophysiological level. You have increased recurrent connection with the circle. Here is the excitation. I like this one. Then on the neuronal segment, you have, if you have more recurrence, you have longer ACW. That's really important. You have longer duration of your activity. It makes sense. If the stimulus circulates, your autocorrelation is longer. Yeah. And then, of course, on the computation, we didn't show this in the data, but remember, it was a safe region. Maybe your self-referential processing is recursive processing, that the stimulus is simply processed longer in these regions. And that makes a difference, and then that relates to the psychological level. Maybe what we experience as self-related, self-specific, may be due to the longer processing time of the stimulus. So here you see a temporal framing of higher order cognitive mechanism. That's spatial temporal neuroscience. So why is that relevant? Give you the example of schizophrenia. So here, same paradigm. Remember the self-morphing paradigm. This was a data set which we did with Denmark, with Josef Panas, who does a lot of phenomenology. And so we were very lucky here. This was done with Karl-Erik Sandsten, who is this guy. And we had a very good time, and we're still working together. So we investigated temporal integration on the paradigm level. We investigated paradigm on temporal integration on the neuronal level, ACW. And we also, in a way, integrated in temporal integration on the phenomenological level, what they call the basic self-disorder. So in the early stages of psychosis, you basically you cannot relate the external inputs to your own self. That's really early psychotic symptoms. Has been very nice described by Huber in Bonn. Early psychotic symptoms, there's also scale, the Bonn scale for basic symptoms. Yeah. Klaus Conrad, some of you may know him, the early tremor stages of psychosis. Beautiful phenomenological descriptions. So now the question is the ACW different in those guys? Yeah, because one key feature of psychosis is they cannot distinguish the internal self from the external input. It's really an internal, external, or other self-environment confusion. They project their own, typical psychodynamically projection for psychosis. They project their own inner onto the external world. So, and indeed, what we observed is a longer autocorrelation window in the schizophrenia. You can see this here. The red ones are the schizophrenia than the blue ones. And that makes sense because they probably put inner stimuli together with external stimuli because their temporal window is to, let's say, if you have only one large window, I wouldn't see the details of the buildings here. So I would probably, you need to show this in the video. Yeah. I'm joking. I would not perceive that little window there different from all the other windows because my window is too big. I don't have the resolution. I need to zoom in. Yeah. If you have shorter windows, you zoom in. If you have longer windows, you zoom out. So you see more, but less precise. Yeah. And then very interesting, because we were very lucky that we had a very nice analysis of the self-disorder. They have a specific semi-qualitative, quantitative interview for that, the ease. And what we saw that the transition from the basic self-disorders, this is a moderation model statistically, to the general negative symptoms was moderated by the timescales. So here, and this is the kind of data I like to see, and we try to develop more and more, that we have an intrinsic connection of psychological, phenomenological, psychopathological symptoms and neuronal data. Yeah, beyond just correlation. It's a key feature of our methodological development these days. So, so I hope I could give you an idea that maybe the self is really related to autocorrelation window, to psychological neuronal mechanism. So, of course, ideally, I would have loved to see a mediation model here, which of course also based on regression, but it's at least a little better than just a simple Pearson or Spearman model. But of course, ultimately, if you have a hardcore statistical view, of course, then I have to give in. Yeah, but that's what we're trying to do. We're also using some Bayesian statistics these days. But it's not an easy one because also the data formats are different. You need to have different sampling rates, or maybe just some formal issues. Yeah, in the behavioral data compared to the neuronal data. Yeah. Yeah, give me a time series of mental data, let's say with 200 data points. But of course, you drive your subjects nuts if you want the 200 data points, constantly assess your consciousness. Yeah. It's a tricky one. And then still, that the sampling rate of your behavioral data is different than the sampling rate of your EEG or fMRI. Yeah, then you probably need to downsample some of your neuronal data. So it's a tricky one. And I haven't really found a solution to that in the literature. Yeah. And it's also hard to get those data. We are trying to do that now. Yeah. And also, it also goes into, let's say, into conscious if you go into the report, no report, because through the constantly reporting, you change your neuronal and psychological features. So it's a really tricky one. Yeah. Yeah. Okay. Consciousness. Here I show you a couple of slides, not many, just to give you an idea. So here we investigated, is the ACW also relevant for consciousness? Here we showed an EEG where we did the EEG in anesthesia, sleep, and coma or unresponsive wakefulness. And you can see a very nice parametric thing. Your ACW becomes longer and longer here, and N3, N2, N1 sleep, and then it becomes sort of intermediate in the REM sleep. And similar, I think I show you here similar findings. This is in anesthesia. The usual ketamine for the experts is a slightly longer, but sevoflurane, a full-blown anesthetic, is much longer. Same here for the unresponsive. So you really see that maybe what I imagine what happens during these stages, that your ACW becomes longer. And I think I have another. Yeah, okay, I come here. Yeah, okay. Here we replicated, it's a different data set. And here we showed again different forms. Calculation, you see again, longer thing. And what I want to show you here, this is the important thing, so that we really had a correlation of your trilateral relationship of your longer ACW mediates the effect of alpha power on consciousness. So we had 3 different measures here. We had a Glasgow Coma consciousness scale, we had the alpha power in EEG, and we have the ACW. And here you see this trilateral relationship that your power ratio in the alpha mediate and on the effect on the consciousness recovery scale is mediated by the time windows. So your time windows is like in our perception, they always operate in the background of your perception. Yeah, the alpha is more in the foreground, direct input gating, all the cleavage stuff, and probably your ACW is in the background. Yeah, so these are probably different layers of your brain activity. So what happens neurophenomenologically? This is a schematic thing, but I think it's very nice. So this goes back to Federico Silio. He's actually a philosopher. He's in Padova now, but he also does neuroscience. He does really good neuroscience. It's fantastic. So here, if you have many time scales, you can account for the time scales of all these different processes. Yeah, the guy catching me. Yeah, but when you lose, let's say, the shorter time scale, it becomes slightly blurry, more blurry, completely blurry. So this is what I assume when you get into anesthesia. You're losing your temporal differentiation in your perception. Yeah, it becomes blurry. Yeah, and that's what probably happened. And this is actually data here. These prolongations, this is all data driven. So here you see how important your time scales are for the input processing. Yeah, because it's like in this, I cannot perceive the buildings themselves. I perceive them through these windows. Same. My brain operates with the input through all its own inner timescales. So if your inner timescales are abnormal, your input processing will be abnormal and distorted. Yeah, that's the idea. So it's basically we're really sitting behind a bunch of timescale. I'm still trying to get a photo online, which I haven't gone. You know, when you have these people who implement windows and they have the different window sizes on their trucks. Yeah, that's basically the way the brain is. Yeah, it's like a truck with all these different window sizes. But please don't quote me on that one. So, okay, so I hope I could show you, the other parts will be shorter, show how temporal features are relevant for mental features like self and consciousness. So now I want to bring you to another layer of our time scales, meaning, so the autocorrelation, depending on the imaging modality, you operate basically shorter, longer millisecond range or second, 10, 100-second range fMRI. But now I want to bring you to phase cycles. So our brain activity is continuously fluctuating. And it's like the wave in the seaside, and you have phase cycles. And you can measure these phase cycles. You do either a fast Fourier transform, or you do a Welsh or other method. And I spare you a little bit the detail, but basically what you do, you have the time series, you filter, and then you calculate the phase angles in the time series, and then you take the derivative of that phase angle. This is a method which goes back to Cohen et al. 2014. And then you basically can also disturb the peak of your frequency relative to your phase angle. And here, so you have the peak in the phase. Obviously, you have higher frequency than in the trough, particularly here in the rise and fall. And basically, you can determine the phase angle. And then I want to now show you, this is another feature. Basically, your phase angle, there have been some nice studies, as far as I know, but you may know this better than I do, in the visual perception field, where they usually use the phase angle and has a relation to visual consciousness. So we are keen on these phase angles because they may be related to conscious contents. So, and here we link this mainly to thoughts. So this is, to my own surprise, we hadn't. So here we had a paradigm, the sustained attention response task. We need to make a response, and then afterwards you get a thought probe. And what we hear in this study, we looked whether there are thoughts related to the task or thoughts not related to the task. It's called on or off task. And here we added another dimension of that. We added, do you have multiple thought content or only one? And of course, no surprise, the on task, focus on the task, were more related to only one thought content. So, and then we measured in the EEG this peak frequency, and that's basically also the phase angle, because your peak frequency is based on the phase angle. So, and what we observed, so this is EEG, obviously. So what we observed that, yeah, it's a frequency. Okay. Yeah, at which time the peak, because it's phase angle based, and whether it's in the peak or trough, it's higher than in the rise and fall. Yeah, but it's usually considered just as a peak frequency, but it's phase angle based, and you can control for that by calculated frequency power. Yeah, and then if the difference is, and that's here the case, the difference disappear in frequency power, then you know it's a phase-driven difference. Yeah, so that's a nice thing what you can do. And here we did alpha and theta. So here you could see in the alpha, so here the brown ones are the on single thoughts. So you see a higher peak frequency in the on thoughts compared to the off. In alpha, here the off thoughts are in blue, and you really get a time. And in the theta band, it was exactly the other way around, meaning your off thoughts are more driven by a slower frequency band in the peak frequency, the phase angles, than the on thought. So in a way that makes sense. If you're faster, your thoughts are also focused more on the input, on the task at the hand. When you're slower, you drift inside and you have other thoughts unrelated to the thought or to my talk now. Yeah. So an important, we also controlled this for frequency power, and then we didn't see this difference anymore. So that really suggests, and we replicated that's now in another experiment, really see that your phase angles are drive your on and off thought content. So schematically, this is the last figure in that paper. You can really see if you have more on single, you have a shift towards higher alpha and lower theta. Yeah, so here you can see the shift. In the off, you have the opposite. You have a shift towards lower alpha, but higher theta. So your brain has a very fine-grained balance to play with its phase angles / peak frequency in different frequencies. And here you can see the schematic thing. It's very well. We continue that. So now here I show you another paradigm, which we just got accepted. So here again we measured, now we did another phase-based measure, meaning we measured the intertrial phase coherent at stimulus onset. So how much is your coherent, your phase at stimulus onset? So this was done in Chinese, as you can in China, as you can see. And he had different tasks, semantic classification, color, and each time he also did thought probes. And then he measured whether on and off thoughts are related to different intertrial phase coherence here at stimulus onset. So again, it's about internal. If you have high external input processing, you have higher phase coherence. If you have lower external input processing, you have lower phase coherence. That's exactly what we could show. Let me see. I think it's in the next figure. If you have, these were the different tasks. So there were also different cognitive loads, but I spare you those details. But the main message is really that the off thoughts show less intertrial phase coherence than the on thoughts. Yeah, and then it also depends whether it was an easy or a more difficult task. So here, and again controlled, it's really that the phase angle / here the intertrial phase coherence is key for mediating different kinds of thought contents. And we have further things here. Yes, this very nice thing. So if you have an easy task, yes, mainly external cognition, you have on thoughts. If you have off thoughts, your intertrial phase coherence is less. You can see this here. You get this, I always call this phase cakes. These are the different phase angles, 0 to 360 degrees. And here you see it's much higher. But if you get a more difficult task, then your off thought recedes because you have to focus more on the task, and your intertrial phase coherence goes higher. So it's a very delicate balance here through internal cognition, off thoughts, and external cognition, on thought, through your phase coherence. Yeah. So, and yeah. So now I show you that this phase coherence is also relevant for schizophrenia. So we haven't done this kind of thought mind-wandering experiment with schizophrenia yet, because this is really all recent thing. But you know some of that because this was in your paper, that we do the phase coherence. And one of the, I think, relatively well replicated finding is that the schizophrenia patients have decreased phase coherence. Yeah, intertrial phase coherence. You see here is a healthy subject. Here you see the schizophrenia. And this intertrial phase coherence measure is basically a variance measure of your phase angles. Yeah, they're more variant and they're more unstable in their phase. You can see this here, very high degree of entrainment, low degree of entrainment. Has been shown in different data sets. We showed this in various data sets. It's replicated by others. So it really seems to be finding here. You see data set 1 and 2, and we had in various studies. So this seems to be, so then from that we inferred that maybe the temporal imprecision is a key moment. I think I show you a couple of slides more. If you want more details on that, I can refer to the website. So, and of course, now you want to have ideally the thought experiments in the schizophrenia related to the phase coherence. So this is what I try to get, but as you know, it's not always easy to get data sets. So come to the conclusion. This is short. So what is the conclusion? So one thing is really, and that you see is a conceptual point, which I think very important because it guides our empirical data analysis and paradigm. So the current standard conceptual background assumption is mental and neuronal features are principally different. Yeah, and then now you project that, and that of course the Cartesian heritage, Descartes says a law, and then you say, of course, there's also different kind of measures for consciousness and non-consciousness in the brain. So you say, okay, there's a special feature in the brain, like information integration, like global neuronal workspace, like higher order processing, like recurrent processing, and that is different from all the rest of the brain. The only theory which doesn't fall into that sort of special edition feature for mental feature is the predictive coding, because that's a theory of the brain. It's not a theory of consciousness. Yeah, and I think we need a theory of the brain to accommodate consciousness. So I'm completely go here with Friston. Yeah. So, and we say, no, we don't say the mental features add something special. Rather, we say, okay, they share something. There's a conceptual background assumption. It's a common currency, similarity. So we say, what is similar between these guys? And of course, you already know the answer. It's clear. It's temporal spatial. So we now speak of neuronal dynamic, mental dynamics. And I think in the next slide, I think I even show, yeah, I show you even that. That's from a very recent paper where we really show, okay, neuronal and mental features, this is all data-driven. Others in own study, let's say you have similar neural variability here and on the attentional fluctuation. We have variability in your phase angles, you have variability in your on and off task thought. Yeah, the duration, the alpha theta peak frequency, the phase cycle. Yeah, very fine-grained tempered thing. And studies I will show tomorrow that we really see that here the timing of your functional connectivity is related to the timing of your movement. I will show that tomorrow. So that's why we speak of a common currency as a conceptual background framework. And now you say, yeah, is this isomorphism? I say, no, it's a correspondence. It's not a one-to-one correspondence. It's a continuum from simple to complex. So meaning my time scales in the brain must not necessarily correspond to the time scales of my consciousness, but the intrinsic relationship, probably because of the scale freeness. Yeah, and also remember the time has a much wider repertoire of time scales than consciousness. It was very limited. Yeah, so and these are various supporting data. So that's basically the background assumption. And you see, when you have this kind of background assumption, you suddenly look for the same dynamic features in neuronal data, in the input series, yeah, the alignment, and in the output. Yeah, so you try to get that also in your mental, you suddenly use for mental time series, you use for mental topographies. Yeah, the philosopher killed me for the concept of mental topography because she said, okay, it's a confusion of categories, the usual thing what the philosophers do. It's a catastrophe. Yeah, so, and there's really indeed evidence, and we have a lot of studies, and that also means you look for slightly different measures. Yeah, I showed you some of that. I could make a whole talk about topography, but I don't want to bother you. And with that, I come to the end of my talk. And that's what I mean by spatial temporal neuroscience. Mental features are spatial temporally shaped. It's not a contradiction to cognitive neuroscience, but it's a wider background umbrella view. Yeah, I do not deny that cognitive science is right, but they only perceive a very small, the upper tip of the iceberg of the activity. Thank you very much.